Okay, welcome to Chapter 11, Raster Analysis. This is my sort of bread and butter. It's most of what I do outside of teaching GIS is in raster world, just because as geoscientists, we have a tendency to want to map and model natural phenomena. So that usually means dealing with surfaces as opposed to points, lines, and polygons. However, they're both used, and you can actually use vectors in raster analysis. There's a lot of information to cover here. This could probably be a bit longer of a lecture than some of the other ones, but let's get started. So rasters have a unique storage model. It's a grid of numbers. And what makes it nice is the fact that you can only have one number. So if you have an elevation raster, that's all you have is elevation, which makes life easier for certain things and a bit more cumbersome for others. And I'll explain that later. Now, each cell has a size, and that's what we call the resolution. So you'll hear me say 10 meter DEM. So that means each cell size is 10 meters by 10 meters, or 100 meters squared. And it stores only numeric values. You can't have text or anything like that. Now, this type of format allows you to do a lot of different analysis techniques, which is what makes it really handy, especially for me and what I do. And sometimes it's a lot quicker. And conceptually, once I start to show you how this works, it makes sense to do how to do this stuff. Now, I'm gonna say this a couple times. It's on a couple of the slides. Because raster analysis relies on distances or areas, you have to make sure that your data is in a projection that preserves these properties. Now, for most purposes, that's not a problem, especially at the level we're working at, at the county level or even less than the county level, that's not a problem. But it's just something you always have to be aware of that, and I've been saying this entire semester, is we utilize the fact that the geodatabase format allows us to get accurate and updated lengths and areas, okay, or distances. So we need those numbers as accurate as possible. And so therefore we want to kind of set ourselves up to make sure that all of our coordinate systems are correct. And there's several ways of doing that. Basically, you make a decision in the beginning of your project and then take a few steps to make sure that that's all there. Now, we've talked about this in the past, but there's two main types of rasters. There's discrete rasters and there's continuous rasters. Discrete rasters store objects like categorical data, like land use. So you have large swaths with the same value. As you can see in the this here, these are all value 10. These are all value 13. Okay, so there's not a lot of variation. There's only three values there. You have value 10, which we'll say is water. You have value 14, which we'll say is urban, and then value 13, which would be um, let's say agriculture. There's some green down here, but it's all covered up. So let's just say there's three values there, and that's it. So you could open the attribute table for this particular raster, and you would see how many values there are, how many cells of each value there are. The other one is the continuous raster that stores numeric data, um, but it's constantly changing. So if you have an elevation, if you go outside, the elevation is always changing, even just a little bit. It might be, too small for the naked eye to see, but it's a continuous surface. It's not just flat everywhere. So in order to best represent that in GIS, you need an array of cells that can continuously change with it. So a lot of times this will mean you'll have, significant digits out to hundredths or thousands, and each cell might be off slightly, or not off, but slightly different from its neighbor, and that's what makes it a continuous surface. Okay, so again, just like on the previous slide, make sure you preserve your distances and areas with the correct projection. You put that on both of these slides. So what can you do with these array of numbers? Well, what we can do is what's called map algebra. And it sounds complicated, but it's pretty easy for the most part, although it can get complicated. Now, when you have these arrays of numbers and you have the same extent and resolution, meaning all the cell sizes match up, each raster is the same exact size and space, you can start to do cell by cell math. And you could see in this example, here's 5 plus 3 you guessed it, equals 8. Okay, just to beat a dead horse here, 4 plus 6 equals 10. So you stack up all of your rasters and you sort of drill down with whatever math functions you need to get at an answer at the bottom. Sorry, thought somebody was there. um, so you can do this by adding, subtracting, dividing. You can do all kinds of things like this, and it doesn't have to be just two rasters. You can do multiple. In my terroir thing, I did 11 at one time to get a final answer, which was my 12th raster. The other thing you can do with this is you can, let's say, take a raster and multiply it by a constant. So um, if I have precipitation in inches and I know the formula to go from inches to centimeters, I just type that into the raster calculator and it does a cell by cell conversion, taking the input, which is precip, times 2.54. So the output is a new raster with each cell now being in centimeters. So it's a raster map algebra, map algebra is a huge part of doing raster analysis. But if you kind of understand what you're doing, it's really not hard at all. And you'll see this as we go along. The other thing you can do with rasters is you can query them just like you could with an attribute table, right? So we can ask the raster a question and get back a yes or no answer. So for example, the purple area in this DEM shows where the elevations are greater than 1400 meters. So I ask the data a question and I get back an answer. If the answer is true, it gives me back everything that's true. And if it's false, it doesn't do anything. It's not met. And this is what we call a Boolean raster. And this is a huge, you can almost think of this as sort of pre-processing, whittling down your data to get at just the area you need. If you don't need anything below 1400 meters, you ask that data a question, you're essentially masking out the parts that you don't need. So I'm not going to go through all of this, but I'll let you take a look at these and go cross-eyed with the Venn diagrams. But what I want you to get out of this is that the and the or are the big two that you're going to think about. Just like we did before um, with rasters, with intersects, the same thing applies here, except now we're using the word and as our Boolean operator, they call that. And you get back just what's in the middle here. So if I have two data sets and I use and, all I'm going to get back is this. That's the most restrictive version, kind of like an intersect in vector world. The same thing applies with the or. If I use the or in Boolean rasters, I get everything back. It's the least restrictive, just like it was with the union tool in vector world. Okay. So when you do run these, you get back yes or no, true or false, 1 or 0. It's binary. The output is binary, which makes it much easier to understand. Okay, so you know exactly what you're dealing with. And it really comes in handy that way. And then you can take, and I'll show this as an example, but you take your raster, you ask it a question, and then you set it aside. You have your, what I call these are the input conditions or boundary conditions. And we'll talk more about that. There's an example as we go. But you'll do this for each one of your rasters in order to whittle down just what you need. This is sort of a pre-processing step. Here's some more examples. And like I mentioned, the AND operator is equivalent to the intersect in vector world, and the OR is equivalent to the union. The NOT is equivalent to the erase function, which is hardly ever used. And then the XOR I've never used in my life, but there might be a reason to use it at some point. Now, the point of doing all of this, again, is to weed out the data you don't need because you have conditions that need to be met. If I'm doing research on a snail, and I know that snail likes a specific elevation with a specific kind of trees and a specific kind of geology, I don't want all of the other stuff with it. So here you can see that this top row here, this is vector world. Okay, this is that analysis being done in vector world, so to speak. Here's the equivalent of it on the bottom row in raster world. You get pretty much the same answer. So how do we do this? We take our elevation, or DEM here, and we ask it a question with the map algebra tool. We say, hey, give me everything, greater than 1400 meters. Great. So the green represents the true version and the gray represents the false. So it's 1 or 0, true, false, yes or no. There's no in between. All right. So then I take that and I set it aside, and now I move over to my trees. Okay. You'll notice these are kind of out of order from the top to the bottom. So I take my dense trees here and I look for just the dense conifer. I isolate those. Okay, now maybe what they're not saying in here that might have been done is up here, here's your dense conifer. That's vector. What they probably did is took that and converted it to a raster to get to this. Okay, so that automatically gives me ones and zeros. I know it's a little weird, and the same thing applies with the limestone. Because you typically your geology is going to be vectors like polygons. So you do a vector attribute selection and then convert it to a raster that becomes ones and zeros, yes or no, either true or false. Now once I have those, I have 3 of them, A, B, and C here on the bottom. Once I have all that, then I can just take them and do the analysis. And I'm not going to explain that quite yet because there's a bit more to show you on that. But then you get this output here at the end, which is a combination of the 3 inputs. So this box is the best place to try to find this particular snail based on the inputs that we gave it: elevation, dense conifer, and limestone. Okay, so in order to get to this, we use the AND operator, which again is very restrictive. So it's like an intersect. It's going to take all 3 of those and only give me back those areas that are coincidental from all 3 inputs, which you can see is not a lot. Okay, so we don't expect it to be a lot because we're expecting that this snail is going to be a bit hard to find because it's very particular about where it lives. So like I mentioned, to do these, you have to use what's called the Raster Calculator tool um, in the geoprocessing toolbox. Now what you do in this is you can see here on the right here, these are all the rasters that are currently in your map, your layers, right? You gotta love the limestone boo. Um, and then what you do is you just double click on one of these and it brings it down here. Like I double click elevation range and it puts it down here. Then I use whatever operator I'm going to use. Now you'll notice this doesn't say and, that's a multiplication. Now the multiplication and the and are exactly the same. They're identical. They do the exact same thing. It's basically an intersect for rasters. Let me repeat that. The and Boolean operator and the multiplication are identical. They do the same exact thing. So I'm taking my elevation range, I'm multiplying it by a limestone boo, and I'm multiplying that times dense trees. So, and then I name my output raster snail hab to show that, that's the final one, the snail habitat. Okay, that's all there is to it. The hard part about doing raster analysis is not this part. This is super easy. It's getting your rasters prepared to be put into the raster calculator. That's what takes a little bit of time, and that's what takes a little bit of practice. Once you have all of your rasters lined up in terms of what your boundary conditions are, your input conditions, then this particular tool is super easy to run. And it's so easy to run, I tell students to run it in 2 different ways, which I'll show you in a second. So here's another very simple example of a Boolean overlay. All right, so we have precipitation areas that are greater than 60 centimeters, and you can see in the blue here, that's 1, and everything else is 0. So the areas in blue match that criteria, everything else does not, and it gets a 0. It's 1 or 0, true, false, yes, no. It's great. Same thing with elevation. So everything greater than 1500 meters is in green in the middle section here, and everything else is a 0. And finally, the lodgepole habitat, which is a type of tree. So we have the 1 and we have the 0. Okay, so those are my input conditions. Okay, I'm sorry, I take that, I apologize. The first 2 are my input conditions. Here's the equal sign, which I totally missed. All right, so I take the first A and I multiply it by B and I get C. Okay, which is the equivalent of and. You'll see the and here, that's the same thing as multiplication. If I put a multiplication sign there and run this, I get the same exact answer. All right. So what I got back was the intersection, the two areas that are coincidental between those two inputs. Now, let's say, for example, we don't want to be so restrictive. What we can also do is we can use the additive Boolean overlay. And that's as simple as changing the multiplication signs in your map algebra tool to plus signs. That's all there is to this. The inputs remain the same. But what the additive model does is it allows for a bit more gradation as opposed to yes, no, it can only happen here, not here. So in real life, the snail might be found sometimes out of its perfect habitat. So the idea is you can also use the additive model with the same exact inputs to get at a bit more of a, okay, here's the best, maybe here, probably not here. And you could see from the previous example, this area in the dark red here with the twos, that was the area that we found with the and, right? It was just there or nothing. But if we add up the ones and zeros, we get areas of twos, areas of ones, which are over here, which kind of like a maybe you might find it here. And then you still have your zeros here because 0 plus 0 is 0, and you're more than likely not going to find that little snail there. And here, down here in the green version, here's a bit more complicated version of going from 0 to 3. You can, change these any way you want. So what I tell my students is when you're doing Boolean overlay, do them both. Because like I said, the hard part is getting the rasters ready to be put into the map algebra tool. Once they're in the map algebra tool, it takes literally seconds to change them from a multiplication to a plus sign. Then you have both models and you can kind of gauge which one probably makes more sense for the type of research you're doing. All right. For me, I mean, mine's a bit more complicated, but it's sort of more of that additive method along with some weights and stuff like that, which we'll get to a bit. But the idea is, with soil, especially, soil's not cut and dry. It's just not, you don't have just starts and stops in soil. There's a lot of gradation in soil. So you have to be able to account for that. And there's actually advanced techniques that do this even better, something called fuzzy overlay. All right. So I teach that in my advanced class where you can use geometric, you can use actually, math functions to model this type of stuff. And we're not going to get into that here, but it was designed for mining, in gold mining actually is where fuzzy overlay, the math for that all start in the concept started coming out of it. Anyway, so the idea is once you have your all your rasters in order, it's super easy to do both the and the plus, or the multiplication and the plus, to see which one best fits for your particular purposes. Now, there are drawbacks to the Boolean overlay, and I just kind of mentioned them a little bit before. If you just do the multiplication, you have yes or no. There's no in between. There's no gray area, if you will. And even with the additive model, it doesn't necessarily always represent the best areas. So what you can do is use what's called weighted overlay, which then ranks things based on its importance in your research, and it becomes more of a realistic approach. Now this is sort of an in between what we just talked about, which was the multiplication and the additive, and what I was also just mentioned, which was the fuzzy overlay. So weighted overlay is kind of in between that, and it's a good approach for most purposes. This is what I use in all my terroir, what I did in my terroir studies, based on previous research. So what weighted overlay does is it allows you to assign a weight to give it a more importance than, let's say, something else. So what that does is says, okay, these are my input conditions and they all need to be there, but this one is way more important and sort of dictates much more of what the outcome should be than this other input. Okay. And those weights, are usually determined by empirical evidence, previous research, things like that. I mean, you kind of know ahead of time which one should and shouldn't be there. Now, the weights all have to add up to 1, which I'll show you in a second. So let's first look at an example. We're going to use a weighted overlay to find the problem of siting a landfill based on these conditions. Okay, so here are my input conditions. Lower slopes are better because we want to minimize bulldozing. Low soil infiltration is important because we don't want leakage into the groundwater. Being closer to existing roads is much better because economically you don't have to build a road to get to the landfill site. And staying away from running water is always a good thing because, again, going back to the infiltration type thing, we don't want to pollute anything. So we have 4 conditions, okay, and we'll rank them 1 to 3. All right, so we have 4 inputs and 3 rankings, and I'll show you that right now. So when you're looking at the landfill stuff here, we have the 4 inputs along the side. We have slope at the top here, slope. We have infiltration, distance to roads, and distance to streams. Now, within each one of these, we've already done sort of an additive model. Okay, we've reclassified these. Okay, so we put 0 to 10, slope is the best at 3, 10 to 20 at 2, and anything greater than 20 is a 1. And we do that for each one of our inputs. For infiltration, low is the best, medium is and high is the worst. And you get the idea. Our distance to roads, obviously we want the smallest distances to be the most important, and then medium, and then anything larger than 1,000 meters starts to become economically prohibitive. And then same thing with distance to streams. Now this one's a bit opposite if you look at this. So 0 to 100 is a 1. We don't want it close to roads. We want it far, or excuse me, streams. We want it far away from streams. So anything greater than 200, we assign a 3. Now those assignments, those 1s, 2s, and 3s, are what's called reclassifying a raster, which I'll get to in a bit. Now the weights must equal 1. Think of them kind of like percentages, right? That's the way I kind of look at them. And if you look at this particular model, the weight here of 0.1 means that it's only 10% of what you need, right? If you multiply that by 100, it's 10% important. Whereas infiltration gets a 0.4 because it's the most important. That's the last thing you want in a landfill, is for it to reach the groundwater. And then you got really bad things going on. And then distance to roads is the second least, and then distance to streams is pretty important. Again, anything with water and landfills, you got to be careful. So you'll notice if you add those up, they equal 1. All right. So that's how a weighted overlay works. It's a bit more complicated than just, 1s and 0s, but it makes sense scientifically. This is a way to at least base your research, or excuse me, your overlay a bit more in the real world in terms of what's really important by decision makers and economics. So when we run this, the landfill suitability index, or LSI, we take, and we're still multiplying, or excuse me, we're adding these together. I apologize. We're multiplying the weight times its input. So in this case, 0.1 times the slope, because the 0.1 slope was the least important of the inputs. Then we add that to the weight times the next one. We add that. So this is the additive model based on all of those particular inputs. And you can see with the diagram here, the suitability is 1 is low, 3 is high. Okay, so you would want to look in the darker areas to site a landfill. Now what's nice about this is it's not just, well, here or here, it's based on weighted inputs. So the chances of finding suitable sites in those dark brown areas is a real possibility based on real world concerns, your inputs. All right, what else can you do with rasters? Well, there's tons and tons of raster functions that go beyond just overlay. You have things like distance functions. With the distance functions, calculates distances from features. I'll show you that in a bit. You can use that to create buffers. You can determine direction of travel to the closest feature. You can create buffers, and then you can create what's determined least cost path, which I'll explain as well. So there's a bunch of other stuff that we're going to talk about as well. So Euclidean distance is something that allows you to take an input that's a vector, in this case streams, or roads, and the output is a raster that gives you distances based on its proximity to the input. So if you look at this diagram, the white areas here are very, very close to the roads, whereas this dark area right here in the middle is far away. So I always say, well, if I was going to build a secluded cabin in the woods, that's where I would build it because it's the farthest away from the roads. All right. Now, it, like I said, the output is a distance. Now, what you can do with that output is then you can reclassify it if you need to create essentially buffers. So once you have the Euclidean distance run, you can uh, run a query or reclassify it to give yourself buffers. Maybe you want everything close to the roads as opposed to far away, or you want to re-rank everything. And we'll talk about reclassifying. We'll get there. But that's what you can do with this output. Now the distance units match the coordinate system. So it's usually feet or meters. So you have to understand that you may need to do some conversions somewhere along the line. And then you can also run what's called Euclidean direction, which is not something I've ever really used, but it'll tell you the direction that you're going in if need be. So this is something I don't use a ton, but it creates a direction raster if you need it, and gives you the direction where you would be, nearest the stream from 0 to 360. So again, this is not something that you're going to use a ton. This is not aspect, which I'll talk about in a bit, which tells you the slope direction. This is Euclidean direction, like which direction you'd have to travel to get to that particular point. So that might be okay, and this might be used in hydrological stuff, but for like what I need it for in terroir, I don't use this very often. So like I mentioned before, once you have the Euclidean distance run, then it's just a simple matter of, if you want to create a buffer, just giving it an input distance. So do you want everything less than 500, which will create these, smaller sort of things, or you could do everything greater than 500, which will sort of give you these voids that are in the gray. It all depends on your needs. Are you trying to, for your buffers, but that's how you can create buffers in rasters. The other option too, and I get asked this all the time, is you can run the buffer tool in vector world and then just convert that to a raster. That you could do it that way as well. There's no reason you can't do that. It's the same thing though. It's still 2 steps either way. If you run the buffer tool, you got to convert it to raster, or if you run the Euclidean distance, you have to run a criteria on it. So it's still 2 steps no matter which way, but it doesn't matter either way. A lot of people have a tendency to run the buffer tool just because it's easier to remember there's a buffer tool than a Euclidean distance tool, but it doesn't matter. It's the same thing. Another thing you can do is run what's called a least cost path. So sometimes when you're doing analysis, the straight line distance isn't always the most applicable. Let me give you an example. So let's say I'm running power lines and I need to go from here on the right to here on the left. Well, if you went as the crow flies across, that would probably be economically prohibitive because you're going up and down and over, topography. So what the program does is it creates, it's sort of like, think about like water travels the path of least resistance. This is the same sort of concept. So to get from point A to point B, rather than going in a straight line distance, which would cost more, this calculates the least cost path to get from point A to point B based on an input, in this case, slope. Okay. So that's how you're able to run things like this and keep the, literally the cost down. That's what it is. You can also create what are called density functions with rasters. And this allows you to, it counts the number of features within a specified circle and divide by the area of the circle to, we've all seen this population density, right? So, it should make sense to you. But there are other things that you could use as, for density. What about well density? If you have more wells in one area than another, maybe there's something going on there, or you might have to change up your methodology depending on how many wells you have in a specific area. So you could create density maps very quickly with this type of thing. There's 2 kinds of density functions. There's a simple density function, which assumes the weight value is exactly at a feature location. So an example that would be like counting impact craters on a planet surface, or what's called a kernel density function, which spreads the values over an area using what's called a Gaussian or a bell-shaped distribution before counting. And that's better for things like population because you don't have it concentrated at a single point, but over representing a whole area. So these are, like I said, these are used for concentrations of things. It could be the beginning of, let's say, a hotspot analysis for crime. Sort of this is not how they do that. That's actually a separate statistical method, but you can gauge what crimes you're looking at based on things like kernel density functions. Another hugely useful technique for using rasters is what's called interpolation, which estimates values in between point measurements. We've all seen this. Every night on the news, you see all those pretty colors on weather maps, and a lot of that is done, obviously they're modeling things, but you can think of it as you have rain gauges, right? They have rain gauges all over the place, and then they sort of based on those rain gauges, they sort of create smooth surfaces to kind of show who got more rain where. I here in Oak Creek, I got way more rain than up in Brown Deer or something like that. Um, so that what that does is it kind of gives you an idea of highs and lows over that surface. And the most common used one is what's called the inverse distance weighted function, where the nearby stations are given more weight than those far away, which makes sense, right? However, this is interpolation in general is a very complex type of technique. I spent about a year really learning. There's a separate toolbox called Geostatistical Analyst and how to create um, surfaces like this, interpolation surfaces with lots of checks and balances. So I know that the output I'm getting it's never going to be the real world. Any type of interpolation is non-unique. It's not going to be exactly the same as the real world. But with the geostatistical techniques, what it allows you to do is run checks and balances to keep what's called the root mean square value, RMS E values low, to know that, okay, this is about as close as I'm going to get with the data I have that's going to best represent the real world. So it's a very complicated subject. One of the things that always sucked about this class is we have to run interpolation as a black box. So I basically say, there's other types of interpolation methods. There's inverse distance weighted. There's Kriging, which is the statistical based interpolation. There's trends. There's natural neighbor. And what I tell my students is if you require that you need it, let's say you have geochemistry data for wells, and you want to create a surface of where the highest lead values are. I'm just making this up as I go along. I just tell you to run all of them and pick your favorite. The unfortunate reality is we just don't have time in this class to go into all the gory details about how these actually work. You're kind of taking some of this as a leap of faith. Now, the ESRI help pages really do explain what's going on, including both the theory and the math. So if you want to learn more about this, and if you're going to do GIS, especially with natural phenomena like geoscience stuff, you're going to have to do interpolation at some point. So it's good to know how to at least create a surface that is as close to real life as possible. It'll never be perfect, but you want to get it as close as possible. Now, there are some other surface analysis tools that you can use with rasters as well. And what I do, I call these one-click operations. Okay, so these four techniques they're tools in the toolbox. You run them, you get an output. Boom, bang, bang, boom, done. So when you're doing your final project, none of these count as an analysis because it's just running a tool. You don't do anything with it other than maybe put it into something else. That counts more towards it. But so things like calculating slope, that's the slope tool. Your input is the other thing with this is all four of these, the input is a DEM. So your digital elevation model can get you all four of these outputs. So you have slope, which is the angles of your slope of your hills, for so to speak. The aspect, which is the direction of those angles. So for example, and I'll talk more about these as we go, in terroir, when you're dealing with plants, you want south-facing slopes, right? And then you have Hillshade and Viewshed. Hillshade is, and I'm going to go through all these, but they're just They're there for a specific reason, and I'll show you those in the next slides. So slope is what you expect it to be, right? Rise over run, tangent theta right equals rise over run. And why is this important? Well, there's a lot of applications where you might need high slopes or low slopes. If I'm doing a landslide analysis, I need to know where the high slopes are. If I'm trying to site a landfill like we mentioned earlier, I want low slopes because I don't want to have to bulldoze everything flat. So it all depends on what you're trying to get at. But the slope tool is super easy to use. You have the option of getting back degrees of slope or percent of slope, kind of like what you see, in the Appalachians with the trucks, 1% slope or 2% slope. So the truckers know, hey, I got to use my brakes a lot. So the idea here is that, you have the option, and most of the time you're going to use degrees. I use degrees most of the time. There are some applications like our subwatershed recharge rate that we'll do at the end of the semester that requires the percent slope. And all that is a drop-down menu here. So right here it says output measurement. By default, it's degree. The other one is percent slope. You choose which one you need. All right, and you get back another raster that shows you, light areas of low slope and dark areas of high slope. Pretty self-explanatory. And then you can take that slope and then reclassify it or run a query on it to get at just the values you need. This is part of the process of getting your rasters ready for a Boolean overlay. I have a DEM, I run the slope. I take that slope and I glean out the values I actually need, and then I set it aside because that'll be part of my Boolean overlay. Hopefully you see a pattern developing here with this. Aspect is the direction of the steepest slope. Again, why is this important? It depends on what you're doing. For me, in the plant world, so to speak, with vineyards, you want south-facing slopes. You want those vines to get as much sunlight as possible. All right. So if I'm siting a new vineyard, I could take everything that faces south, from southeast all the way to southwest. I could just take everything that even has the word south in it, so to speak, and then query that once I run the aspect tool. So I run the aspect tool, I get back all the southerly facing slopes, and I set that aside for a Boolean overlay. So again, it all depends on your needs. This one's more applicable to what I do than, let's say, the Euclidean direction one that I spoke of earlier. Hillshade is just an angle of the sun to give you sort of that look of topography, ruggedness. It's strictly a picture. That's what you need to understand about the hillshade. The hillshade is strictly there at being able to display your map more. You can't do any analysis. The output of a hillshade is 0 to 255, which is black to white. So that's really all it's for, is a visual thing, but they come in really handy and make your maps look a lot nicer, to be perfectly honest with you. Now Viewshed is a bit different. Viewshed is an actual technique. If I work for the rangers out in Wyoming somewhere, and we got the budget to build another fire lookout tower, I want to be able to place that lookout tower so it has the least amount of overlap with any other one. So what I can do is I can pick a point, okay, this point here, I can pick a point, and everything in that orange color is what you can see from that particular point. All right. The other example I use is kind of silly. If money was no object and I'm building a mansion on the top of a hill and I want the best possible view, that's where it would be. Or that's what I'd be able to see from that particular vantage point. So you can see that there are some applications of this, but it's not something you're going to use a ton. Now, along with all of the other stuff I've been mentioning, there's also statistical things that you can do to your rasters as well. Neighborhood statistics operate on a neighborhood, so it's sort of a group of cells or a window around a target cell. So you can see here, this thick black line, this is my window, okay? And everything inside of that window, this is a 3 by 3, so that you have this one middle value here. So it's going to take that value, okay, and we'll say it's going to average all of the values around it and assign that value here. So if you take all of these and average them up, you get 2.5. What does this mean? You've probably all done this, maybe not, a little bit. This is the same sort of thing that occurs if you're using like smoothing algorithms, smoothing out images. Let's say you take a picture and you want to kind of smooth out your face a little bit, filters in Snapchat, that kind of thing. That's what this is essentially doing. You're averaging out the cell values to create a smoother image. In this case, a smoother surface. Okay, they're typically squares, these thick lines, the windows are usually squares, but that doesn't always mean that. And you don't have to always do the average here, the mean. There are other options. You can take the variance, you can do the standard deviation. It depends on your needs. This can get very complicated, but in a nutshell, for the purposes of this course, just understand that these moving statistics, these moving window statistics, is a smoothing algorithm that allow you to sort of it removes spurious values. And you'll see that as we go along. There's a couple of examples here. So there's two kinds of neighborhood functions. You have the block functions, which I just mentioned, where you have this block of values. You have a block of values here. It does something to that block and then moves to the next block. Okay. Actually, that's not the previous example. The previous example is the focal one, where you have sort of a moving window where it moves one at a time and creates a value for the center and just keeps going along like that. I apologize. So the previous example was a focal neighborhood function, not a block neighborhood. All right. So in the block neighborhood, cells are never in more than one neighborhood block whatsoever. Whereas in the focal neighborhood function, each cell is evaluated in multiple neighborhoods. So again, you could kind of think of it, if you go back to the word smoothing, the block neighborhood is going to smooth it over, but the focal neighborhood is really going to smooth it over because you're averaging and averaging and averaging every single time that window moves. You're averaging more and more. So here's an example. So if we take this first raster here, which is a land cover map, it's pretty complicated. There's a lot going on there. All right. Um, Sometimes the ultimate goal for this is, hey, at some point I may need to convert this to polygons. If I take this raster A here and try to convert that to polygons, it might work, but you're going to get a mess. Or it could just blow up your machine, so to speak, because there's just too much information to convert there to polygons. It could take forever. So what you can do is you can run a majority neighborhood statistics, in this case in a 4x4 cell window. So what that does is it takes the cover type that's most frequently in that neighborhood and assigns it to the target cell. Okay, so here's the focal one here. You could see it's pretty similar, right? It's pretty similar. It's a more fine-grained version, or a more abstract. How do I say that? It's a more smoothed out version of A, but it's not super smoothed out. Okay, but there's still a lot of information there. And then if you use the blocks, you could see it really gets blocky. Okay, sorry, I had to, the blocks get blocky. Um, However, that particular raster, this if the resolution isn't the issue, if it's just kind of knowing where the land cover values are, the letter C one here, the third one on the one on the right, is perfectly fine and will convert to polygons much easier than B or A. So it all depends on sort of your limits as to how much you want to smooth it out. The focal majority have a tendency to keep things in place a bit more, keep a bit more of the information, because again, that window is moving very slowly. Whereas the black one, it's going chunk, 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 and that's okay. That's okay if that's what you need. Now, rasters can be converted to polygons, and that's what I mentioned before. So if you try to take pane A here, if you try to take that and convert it to a raster, or excuse me, a polygon, like I said, it might work, but the file might be huge, not that big, but it could be big, or you're going to get millions of polygons, and then you're going to have to try to dissolve it and all this, and it can really bog down your machine. So what you would want to do first is run a pass or two of the focal majority tool, and that smooths it out, but you still can see that where the bulk of the areas are. You're not losing that much resolution. Now, if you're far enough out at scale here, you can see there's like a whole lake there and some other stuff, maybe a whole city. At that scale, the the pane on the left or right, pane B is perfectly acceptable. Now, if I'm at the vineyard level, I probably wouldn't want to do this. But then again, if I'm at the vineyard level, I could probably take the land use and convert it directly to polygons. So a lot of this is determined by the scale at which you're working. Okay, if you're at a very small area of scale, a large scale map, small area, you could probably get away with just converting it to polygons. But if you're dealing with larger areas, small scale map, you might want to run this to help cut down on your processing time, especially when you get back to vector world. Another hugely helpful set of tools is what's called the zonal functions. Um, I always tell this story when I first started learning. The very first year I taught this was in 2008, a long time ago. I had to teach this, and I honestly didn't know what zonal functions were. So after that particular disaster of a semester, I went back and I just poured over all this stuff to try to understand. And what I realized is zonal functions are very handy. What it allows you to do is it's like a neighborhood function, but it allows you to sort of combine either two rasters, excuse me, or a raster and a vector together to get back data and get back something that you would never have been able to do otherwise. And I'll show you this as an example. So there are 6 zones. A zone is a set of cells or features with a unique value. In this case, there's 6 zones. They're geologic units. So this could be a raster or a vector. Okay, it doesn't matter. And the zones do not need to be contiguous. So you can see like there's green over here, but there's also green down here, right? They don't have to all be touching. That doesn't matter. Okay, but they just have to all have the same values. So the green values of both of those need to be the same. So you can use what's called zonal statistics. And this is, I love this tool. So on the left in pane A, you have the watershed polygons, and those are vectors. Those are polygon vectors. So that defines the zones. All right, so we have the feature ID field in there, which is a unique identifier, so we know exactly where the values we're going to get back are going to be placed, right? So you want to have sort of a unique identifier. Then the zones that were applied to a slope raster, all right? And what that allows us to do is take the polygons and get back the average slope for each one of those polygons. Wow. I mean, that when I first started learning this, I'm like, that's amazing, because what that allows you to do is sort of get the best of both worlds. I have the areas of my polygons. Okay, so sometimes you need to know the areas, but now I can take that, combine it with a raster, and get back statistics, in this case the average slope of a watershed. What does that do? Well, that tells you, okay, there might be more runoff in an area in a watershed with a higher slope value, or average slope value, than a lower one. And that those type of things, this wouldn't have been able to be done without this particular tool. It's a hugely helpful tool to be able to combine rasters and polygons, or two rasters together, and get back values based on from one zone to another. It's very powerful technique. Now, I mentioned a while back that we'd get to the Reclassify tool. Now, a lot of times what you need to do is you have to know ahead of time what your input variable, I call them boundary conditions, are going to be. If you go back to the weighted overlay example, they had 4 boundary conditions. They had the slope, they had infiltration, they had distance to roads, and distance to streams. Now, within each one of those, they characterized them in three slots, and then gave them 1s, 2s, and 3s. To get to that, you have to reclassify the raster. So if I'm using, so in this example, you can see here's the Reclassify tool. The input is elevation. So elevation is a numeric value. All right, so here is my values, my start and stop values. All right, so if all I care about are the values of between 1200 and 1600, I assign that a 1. So essentially, I'm manually assigning the true values, or the 1 values, the yes values, as opposed to the no values. Now, you could do this with the Raster Calculator. This is not the best example of this. The better example would be to create sort of a gradation thing like they did in the weighted overlay example. So maybe The 12 to 16 would be a 1. The 16 to 2000 would be a 2, or vice versa. And then everything down here would be a 3. So you would change that to 1, 2, and 3. And you manually click in there and change these values by hand. What that does is that creates a new raster so that you get back with the values that you want. Let's say 1 zeros or 1s, 2s, and 3s at the cutoffs you require. So in this case, my cutoff is 1200 to 1600, and I assign that a 1. So the Reclassify tool is used a ton in raster analysis. It's a sort of a manual way of creating the breakpoints you need to take that raster and put it into an overlay down the road. Now, all these tools I've been talking about, every single one of them, is found in the Spatial Analyst toolbar, or tool set, excuse me. This is called the Spatial Analyst extension. This is where my bread and butter is. I use this more than anything else. And if you look at some of these, here's your density functions, your distance functions, extraction, your extract by mask I use all the time, which is basically a clip for rasters. I think they've changed that in Pro though. I think there actually is a clip for rasters tool. The hydrology tools, the interpolation, here's map algebra. I've used multivariate. I've used this. Oh, down and down and down. I've used all your surface stuff is in here. Your hillshade, slope, aspect is in the surface toolbox, and then your zonal statistics is here. I've used all of these, almost every single one of these. This is my sort of my tool set that I use in the geosciences because this is the type of stuff that we do. However, in the real world, it costs a lot to get all of these tools. You have to pay extra in the real world for every toolbox you add on. So if I went out in the real world and they can't afford Spatial Analyst, what I would probably have to do is switch to QGIS, which is an open source GIS program, because this program costs a fortune, unfortunately. But I just wanted to show you that, yeah, Spatial Analyst is where almost all of the tools that I've been discussing in this particular chapter are found. Another key thing that you have to consider when doing raster analysis is your environment settings, particularly 4 of them. The workspace, the processing extent, the cell size, and a mask if you're going to use one. You want to set these up ahead of time in your project to ensure that everything's consistent as you go forward. So the workspace settings, that makes sense, right? You want to, anytime you run a tool in the Spatial Analyst toolbar, you're going to get back an output, a raster output. Well, you want to always know where that's going. So you set it up ahead of time, say, hey, put all my stuff in this particular geodatabase so I know where to go find it, all right? Sometimes what you can do, you'll see there's current workspace, and then there's Scratch Workspace. Now that's an old thing that was used. You'll notice they're both the same, pretty much. Is that the Scratch Workspace is designed for temporary raster files that are created sometimes during tools. So sometimes it'll create a temporary raster, and you won't ever see it. It'll be there and then gone because you'll get the output. Think of it as sort of an intermediate step for the program, but the program has to be able to put it somewhere, even temporarily. And by setting it up with the Scratch workspace, you ensure that the program has the permission to do so. Otherwise, it might try to put it in a spot you don't have write access to on your hard drive. So for the purposes of most projects, the current workspace and the Scratch workspace should be the same. The output coordinates, I typically use these, although they're saying now it's a good idea not to change the coordinate systems during processing. What I tell people, and it says it should be blank for raster analysis. That's not totally true. When you're starting your project, you're going to pick a coordinate system, and usually that coordinate system is based on what the bulk of your data is already in. Okay. If I have a DEM that's in UTM zone 15N, I'm going to use that because I know the bulk of my data is going to be derived from my my DEM, my hillshade, my slope, and all that, everything's going to be derived from my DEM. I would set this to what my DEM is. So it's not changing anything. It's just ensuring that all of the data is in the same exact coordinate system. What they're saying here is don't set it up so that the output coordinate system environment setting is reprojecting things for you. You can put it in there as long as it's the same coordinate system that everything else is in. I hope that makes sense. So I usually set this to whatever the coordinate system I've decided on, usually what my DEM is, and then go forward from there. What you don't want to use this for is an alternative to the project tool, because then it's going to be running things in the background that you don't want. The other option that you can set is the processing extent. I typically don't use this a lot, and the reason being is for the class, typically you have what's called an area of interest. And for our class, it's usually a county. Let's say I'm doing a project in Dane County. So Dane County is going to be my extent. It's already set up for me. And if I've done my pre-processing correctly and I've clipped everything and I've extracted everything down to the shape of Dane County, I really don't need this setting. So I don't use it too much because I do everything, I get all my ducks in a row before I start running the analysis. All right. So you have to be a little, you can use this, it's fine. But for most projects, I don't, because I already have everything whittled down to my area of interest already. The cell size setting is important. Again, I tell my students the cell size should match your DEM. If you have a 10-meter DEM, you should set this to 10 meters. Every tool you run will be 10 meters. If you have a 30-meter DEM, okay, it should be 30 meters. You can't downgrade, meaning if I have a 30-meter DEM, you can't put 10 meters in here. It doesn't work. So you have to, the cell size should match your DEM, whatever one you happen to get. So if you're using LiDAR data and it's 2-foot resolution, that's what you put in there. Although you better have a good computer to do that. All right. So what that does is that eliminates resampling. So you don't want to keep changing things in the background. You want to keep everything consistent. So setting it to the same exact thing as your DEM, because a lot of the stuff is derived from your DEM, going forward will make life a lot easier. Another option that you can use is what's called a mask. All right, so a mask is sort of getting rid of everything outside my area of interest. Again, I don't use this because I've already clipped and cut and everything down to my area of interest already. So therefore, this is an option, okay? But I prefer to just, like I said, clip everything down to what I need it to. So one of the things you have to take in account with rasters is something called a technique called resampling. Now, when you're doing raster analysis, all of the cell sizes have to match. And if they don't, then they need to be resampled so they do match. The problem with this is that this is pretty much done in the background without you even knowing it, and it's going to default to the larger cell size, which means you're going to degrade your data. All right, and you can lose your accuracy with that. So I tell my students to start with your DEM. If you have a 10-meter DEM, then set your cell size to 10 meters. Then any tool you run is going to match that cell size, and then that way everything's consistent, and you're not trying to downgrade or upgrade anything going on. If you have a 30-meter DEM, then use 30 meters. I don't make it a requirement for a 10 meter. It's just that 10 meters is now sort of the de facto standard. If the only DEM you can find is 30 meters, then by all means, go ahead and use the 30-meter DEM. It doesn't matter. But the thing is you need to be consistent. And it's if you start right away with the DEM and you know the cell size and you understand what's going on, you can set up your environment variables and ensure that every tool that you use is the output will have in this case, let's say 10-meter resolution. All right, so there's a couple of different techniques that resampling can use based on whether it's a discrete or a continuous raster, but we're not going to go into all that. I believe it's in the book. There's bilinear, cubic convolution, nearest neighbor. But just make sure you understand that, try to avoid this being done without you knowing it. And by doing that, you just set it up right from the get-go with the cell sizes in your environment variables. All right. So there's a ton of information in this chapter. I mean, this is where I live, so to speak, for GIS. There's so much you can do. There's so much I haven't even discussed with when it comes to raster analysis, and you can do a lot with rasters, just like you can with vectors. In the geosciences, when you're modeling natural phenomenon, rasters are a much more conducive method than vectors are. Most of the time, any vectors I need, I end up converting to rasters, or vice versa. It depends on the tools needed. Just know that you can do that, that it's perfectly okay to run a buffer tool in vector world and convert it to raster, or run the Euclidean distance tool, uh, use map algebra and convert it to a vector, although that doesn't really make sense, but you get the idea. You can go back and forth, but the more complicated the raster, the more care has to be taken to ensure that you don't kill yourself with polygons. That's where like the focal majority and the neighborhood functions come in. So there, like I said, I could go on and on and on about how rasters are, raster analysis is what I do. And in the advanced class, we talk about the weighted overlay a bit more in terms of terroir, and then the fuzzy overlay, which uses mathematical functions to give you even more gradation, because especially in geology, like gold prospecting, it's not cut or dry. So you want to be able to get that sort of fuzzy fuzziness in terms of, where is the best possible place over an area, or over a whole gradation to find gold, for example. All right, so that's it for chapter 11. We have one more chapter left, and it's a brand new chapter that I've never even covered, called Sharing with GIS, right? I think so. And how you can share your maps, and it's going to be new for me as well. I'm going to have to review those slides, but I'm looking forward to it because it's the way GIS is done now. So much is done online now that I could see in a couple of years that we will be incorporating more and more of that into this course. You have to, okay? I approached this course based on a lot of analysis because that's what I do. But I do realize too that you have to understand what other people are doing, and going forward, trying to utilize these tools that allow you to share data, share maps, and sort of get your research out there, so to speak. All right, that's it for chapter 11. Take care. We'll see you in chapter 12.